Okay, so we're really going to start, especially the last 3 units. There is a unit 9, but I kind of don't worry about that really a lot. We'll see what we do with it. We want to get the first 8 units done for sure, and we will. Okay. Remember I told you that there's sort of 3 main components of statistics. We've basically finished 2 of them. Collecting data, which was essentially unit 4. Analyzing data, which was like the first 3 units, along with sort of like probability. We needed to know some probability to help us with the last main component, which really is sort of the, the meat of statistics, and that's making conclusions. So we're going to move into problems where we're not just sort of saying, okay, well, how would we collect this, and what are the problems with collecting it this way, and how are we going to analyze it? What are all the measures we're going to use? We're going to come up with answers. Okay, and it's all really based on something that's called sampling distributions. Okay, when we want to know something about a population, generally the population is just too big to ask everybody, or if it's an object, to test everything. Because if we want to ask a question, usually we want to ask it of several thousand people. And we just can't get to all those people. So we have to choose a sample, which we have talked about. Okay? And out of that sample, we want to get conclusions that we can transfer to the population that we're talking about. Okay? And like I said, we have talked about it a little bit. Like we talked about it in Unit 4, saying that, if you get a random sample of people, you can take your conclusions and generalize it to a population. If you randomly assign them to groups and do an experiment, that's when you can do cause and effect. So we've addressed it a little bit. Okay? So, and the best way we learned how to sample was random. But randomness also includes an element of chance. Okay, so we can't, and I'm just sort of summarizing this, we can't guarantee our conclusions are going to be correct, but we can guarantee that they usually give correct answers with a certain degree of confidence based on probability. Okay, so like you would ask yourself, how often would this method give a correct answer if I used it many times? And if it comes from random sampling, and we use the laws of probability, we can get a pretty good idea. Just as a little bit of review here, terminology relating to populations and samples. Okay, when we have a measure of a sample that we take, such as the mean or a proportion or something like that, that describes a characteristic of, that's for a sample. That measure would be called a statistic. So a statistic is a number that describes some characteristic of a sample. So we would say sample mean, sample proportion, sample standard deviation. A parameter is a measure of a population. So we would say population mean or true mean. Population proportion or true proportion, because that's the actual proportion that prefers something in the population. We're really going to go big on means and proportions. So when we calculate a sample mean, we call it X bar. And then when we refer to the population mean, we use For sample proportions, if we are talking about a sample proportion, we use p hat, but a population proportion is just p, lowercase p. Standard deviation for a sample, we say SX, and it estimates the Greek symbol for segment, which is the population standard deviation. So just as an example, the Gallup poll, the Gallup poll asked 515 randomly selected U.S. adults if they believe in ghosts. Of the respondents, 160 said yes. Identify the population, parameter, sample, and statistic. What's the population? All U.S. adults. What's the sample? 515 adults. What are we attempting to try and determine the proportion of the population that believes in ghosts? Right? That would be the parameter. So the true proportion, because samples aren't going to match up to populations exactly. Okay? We can be confident, but it's not going to be perfect. So true proportion, which would be just a p, of U.S. adults who believe in ghosts. That's what we're ultimately trying to get to. And then we use the sample proportion, which in this case would be the statistic. Well, we know the sample proportion. It's p hat, and we can calculate it because we were told in that sample of 515, 160 believed in ghosts. So we have that exact value for that sample. Okay. Question becomes, is this representative of this? And there's things that we have to do in order to state that it is with confidence, or state that it isn't with confidence. Okay. Now, what we're going to do in this unit is we're going to deal with problems where we're given population information and we're going to calculate sample information. But that's not normally the way we do things, right? We normally are trying to find out about the population, but we want to see how a sample behaves in relation to a population before we go in reverse. One more example. So here's a couple of scenarios. For each case, they're either the numbers in bold are either a parameter or a statistic. State which it is. So on Tuesday, each bottle of Arizona iced tea filled in a plant was supposed to contain an average of 20 ounces of iced tea. Quality control sampled 50 bottles at random from the day's production. These bottles contained an average of 19.6 ounces of iced tea. Okay, so we've got 20 and we've got 19.6 in bold. What does the 20 represent? A parameter or a statistic? A parameter, because it's the population, right? Because it's what the population, the proportion that it's supposed to have. So it is a parameter. That's what's supposed to happen. But when we took a sample of 50 bottles and measured the number of ounces in each bottle and averaged them all out, we got 19.6, which is a statistic because it's the sample mean. It's the mean of 50 bottles, the amount of liquid in 50 bottles. Second example, on a New York flight, on a New York to Denver flight, 8% of the 125 passengers were selected for random security screening before boarding. According to the Transportation Security Administration, or TSA, 10% of the passengers at this airport are chosen for random screening. So we've got 8% in bold, and we've got 10% in bold. What would 8% be? A statistic. Because we're taking a portion of the population of one flight, right? We're not screening all the entire population of 125 on that flight. We're only screening 8% of them. Therefore, it's a statistic. How about 10%? You sure?
Yeah.
Just because one is a statistic doesn't mean the other has to be a parameter.
But then I think, that's like an average.
Yeah, it says 10% of the passengers at this airport. Okay, so it's another statistic. Because we are taking a percentage of the population and measuring by screening. Okay, so just be careful how you read those. Okay. What's this whole idea of a sampling distribution? What it means is you have a population and there's certain information about the population. Maybe there's the mean income, the mean, no, I don't want to say it like that, mean height or mean weight or things like that. The proportion that are female, the proportion that are male, the proportion that prefer this over this, whatever. Okay, there's all sorts of things that we can measure. And so what we do to try and find that measure, if we don't know it, is we take samples. And we usually take more than one. Okay? And then we take all those samples and we make a sampling distribution. And we study that sampling distribution that allows us to make a conclusion about the population. Okay? The things we have to remember when we do this, something called sampling variability. Okay? That different random samples of the same size from the same population will produce different values. So how many of you are in this room? 10. Okay, so let's say I wanted to measure the average height of students in my statistics class. Okay, but I didn't want to do all 10. So I was going to take a sample of 2. Okay, I'm just going to take 2 of them. I'm going to measure the height of both of you. I'm going to average it out. And then I'm going to see, okay, if I did that sample several times over, what is it going to look like? How many ways could I, and I'm going to get different results every time, aren't I? Like if I pick 2 of you and then a different 2 of you, your average height is not going to be the same. That could be close, could be different, okay? But if I take several pairs of 2 of you, and if I average them all, I should get something near to the true height, the true average height in the class. Okay, so sample variability means in each sample that I take, they're not going to be the same as the others. If I were to take a sampling distribution, if I were to take a perfect sampling distribution, I would take every possible pair of U10. Okay? So how many ways can I do that? Well, how many ways can I choose 2 students from 10? This is where we do that combinations again. So 10 choose 2. So if I do 10 choose 2, there's 45 different possible combinations. There's 45 different pairs. Okay? That's a lot. And that's a very simple example. We don't do things that small in statistics. Imagine if you want to sample 1,000 people from Winnipeg. And let's say there's 750,000 people in Winnipeg. 750,000, how many different samples of 1,000 can you choose from 750,000 people in Winnipeg? It's going to be a scientific notation number. Oh, it's going to be an overflow. I don't think I can even get that. Let's see if I did 75,000. Oops. How many different ways can I choose 1,000 people from a population of 75,000? Nope, overflow again. It's just too big. Right? So that would be a perfect sampling distribution. So the sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size. And like I said, for large populations, it's just too difficult to do that. So we make approximate sampling distributions. And like I said, when we get this sampling distribution, okay, we can see from the sampling distribution whatever we're measuring is considered normal and what is considered not normal. And it will help us answer certain questions. So let's take, first of all, we're going to take this example. So to determine how much homework time students get in class, Mrs. Lynn has a student select a simple random sample of 20 chips from a large bag. The number of red chips in the random sample determines the minutes of homework the class gets to work on. Mrs. Lynn claims there are 200 chips in the bag, half of them are red, or 100 of them are red. When Jenna selected a random sample of 20 chips from the bag, she got 7. Okay? Does this provide convincing evidence that less than half the chips in the bag are red? Well, first of all, what's the evidence that we're looking at? What's the evidence that leads us, is there really half, or are half the chips red?
2 samples.
What's that?
2 samples.
2
Samples.
2 samples.
Never mind.
What happened in this?
7.
She got 7 out of 20.
Yeah.
Right. Which is not 50%. Is that what you were trying to say?
Yeah.
Okay. Jenna's sample proportion seven out of 20 or 35%, not 50%. So that leads us to initially believe, well, maybe it's not half red. Well, what are 2 possible explanations for this?
So you put that on the wrong chips.
What's that?
Just her sample didn't have enough chips. Doesn't mean that the whole bag. You know what I mean?
Are you going to get exactly 10 red chips every time you pull a sample? Because of, no, because of sampling. Come on, guys.
Variability.
Because of sampling variability. Okay? One, you didn't get 50%. I don't know. Yeah, I know. You can make them edible if you like. Okay? What's the other possible explanation? Mrs. Lynn is not telling the truth. Mrs. Lynn is not telling the truth. Oh boy. Getting to see grandma. Okay, so we're in a bit of a pickle here.
Yeah.
So to get around this, we're going to run what's called a simulation where we're going to take 500 random samples of 20 chips from a population of 200 that does have 100 red and 100 blue. Okay? So imagine, like, and we do this by technology, but imagine you've got a bag that everybody knows it's got 100 blue and 100 red in it. Okay, you're going to pull out 500 samples of a size 20 each and measure the proportion that are red. And this is what we got. Okay. Why were we getting different results? Because of sampling variability. Okay. So how many times did we get a really low result? Really just once. These are low, but perhaps not unusual. This could be considered unusual, but as we move towards the center, it's less and less unusual, right? And it kind of tells us that, well, the average, if we averaged all these out, we're up here, 50-50. Okay? So there's one dot here. What does that mean? Tell me what that dot represents in the context of the problem.
80%.
One sample had 80% red chips. Yeah. Now remember, Jenna, she got 35%. Well, if we look at 35% in the sampling distribution when we ran a simulation, does it look unusual or did we get it a few times? We got it a few times and we even got proportions less than that. Okay? So, not really. Because the simulation produced a fair number of samples that were 35% red or less. So based on this, is there convincing evidence that half the chips in the bag are not red? Or sorry, that less than half the chips in the bag are red? Obviously, it's the same thing. So no, I'll just leave it at that because I really did the explanation there.
I think it would be kind of unsanitary if they were edible chips.
What?
I think it would be kind of unsanitary if they were edible. Yeah, but like staying with like topics.
All of it, like,
Like,
are you talking red pudding chocolate or the blue type is, yeah. These could be toppings, these could be toppings.
The probability.
But then that also creates variability because one of them gets.
And what of these?
Walking with the.
Let's say jam sample was this, 15%. Would that provide convincing evidence? 15%. Let's go back to the simulation. How many times did 15% or less occur? Once out of how many? 500. That's very low. That means that happening is, very unusual. Sorry, I had my podcast going on here and it jumped back in. Okay. Yes, because only one of 500 samples had 15% red chips or less. Which is very unusual. So really, and we're going to be dealing with this a lot when we do the rest of the units as well, is like we can prove something if something unusual happens. If nothing unusual happens, then it's kind of the status quo. So if somebody makes a claim about something and we find that it's not really unusual when we run a simulation, okay, then we just basically say, okay, well, that claim I guess is true. But if we get a really unusual result, then we can say, well, maybe not. Okay, I really talked about this when we did the chips example, so I'm not going to go through all of this. This was the population distribution. That was like what actually is. Okay. And then what we did to see if this was actually the truth was we took several samples. And in each sample, we measured the number of red, or the proportion of red, and then obviously the proportion of blue, if you know the proportion of red. And then we took all these samples and we made a sampling distribution. So, you know, each one of these represents, oh here, this would be 40%. So this sample was 40%. So that means that this one would be a dot in this line. The 55 would be in this one. The 65 would be in this one. So just be aware of the different distributions. Okay? We take these to create this to help us make a conclusion about this. That's basically what we do. And that's basically what all that says. So I'm not going to go through all of that. Okay, how do we describe sampling distributions? Well, the way that we describe other distributions at the beginning of the year. Measures of center, measures of variability, as well as shape. Okay? So, but remember, we're talking about a sampling distribution. So when we measure the center, what we want is an unbiased estimator. That means, is the measure we're using going to correctly measure the population? If it doesn't, it's not a biased, or it's a biased estimate. If it does, it's an unbiased estimate. So going back to this example, we knew in the population that the proportion was 0.5, or 50% red chips, right? When we did the sampling distribution, when we created this, okay, what measure were we using? The proportion of red, okay? Was the proportion of red, if I average this out, a good measure of what the actual population proportion was? Like, what was this centered around? What is this centered around? 50%. What's the actual population distribution of red chips? That means this is a good estimator, or an unbiased estimator. If I got a result that looks something like that, that's not a good estimator, because what is this centered around? Around 0.7. But we know that's not the percentage of red chips, which means that this measure would not be a good estimator of the population parameter. Okay? That's essentially what biased and unbiased means. So just to summarize that up, a statistic used to estimate a parameter is an unbiased estimator if, when we average out its sampling distribution, okay, it is equal to the true value of the parameter being measured. And like I said, that green one that I showed you, okay, is biased if its mean is not equal to the true value of the parameter, the population parameter being measured. Now, obviously, we're not going to be using biased estimators. We're going to be using unbiased estimators. And really, the unbiased estimators that we are going to be using in the remainder of this course are mean and proportion. Okay? Because those are sort of the majority of questions we can answer in statistics. Variability. Okay? Essentially, what I want you to get out of this section, and like I said, there's a lot of text in this lesson, but I'm just trying to summarize it. Okay? The smaller the variability, the better. We know that by now. Okay? What are some ways that we can make it smaller? We can make it smaller by increasing the sample size. Not the number of samples we do, the sample size. So, for example, here we are discussing the proportion of, I assume, let's say US adults that watch Survivor. And we know that the population proportion, P, is 37%. Okay? But then we draw, like I said, we get a sample size, or we get a sample 400, and we draw sample sizes of 100. We draw 400 samples of 100 each. And we measure the proportion of those 100 that watch Survivor. And we got this, centered around 37, which shows you that sample proportion is a good unbiased estimator of population proportion, but it's fairly spread out. What happens if we did the same thing Okay, still 400 trials or 400 samples, but this time each sample size was 1,000 instead of 100. Notice we're still centered around 0.37, but it's much tighter. Okay, so one thing I want you to get, basically the one big thing I want you to get out of this, increasing the sample size reduces variability. That's the big thing I want to get you, I want you to get out of this. Within reason, which we'll talk about later. Because if your sample starts to get too big, we're not going to be able to do some calculations that we want to do. We'll talk about that later when we get into the other ones. Okay? So again, that's basically summarizes all of that. What's the ideal? What do we want? Well, this is what we want. We want something that's unbiased and small variability, small spread. Okay? Which of these, if we were shooting at a target, would be the ideal one? D, right? Because we are accurate, and if we do it over and over again, we are precise. Okay, so this has low bias. I won't say no bias. It shouldn't have said no bias, because there's always going to be a little. And low variability. This is the ideal. This is what we want. These other ones, well, this fairly low bias, because you are kind of around the center. Obviously not as good as this, but not very precise. Pretty spread out. So higher variability. This one, okay, well, we're way off target, so that's high bias, but it's low variability because it's grouped tight together. Okay, I mean, this would be an example of an unbiased estimate, or sorry, a biased estimate. Here, this is the worst one. We're off target and we're really spread out. Okay. High bias, high variability. But just remember, this is the ideal. Oh, sorry, D is the ideal. So just as a little bit of a practice, showing you in a different way visually, which one of these distributions would you say is the best in terms of bias, low to none, and low variability? B, this one here for sure. Because it's centered around the population and it's pretty tight together. Okay, which one would you say is the next best? Just out of curiosity. C? Is that what you said?
Yeah.
Yeah, C. Because we are kind of centered around the population, but it is spread out. But it's better than this. Okay, this is probably the worst one. And then this would be the second worst, this would be the second best, and this one, this is the ideal, so B. And we want B because it's going to have low bias and low variability. Okay. So this is kind of an introductory lesson to what sampling distributions are all about. From this point on, we're going to start using them. And we're going to start using them in examples that involve proportions and means. We're going to do that a lot.